Welcome to the stoichiometry tutorial number 6. This tutorial covers percent yield. You will need the usual periodic table, solubility chart, a calculator, a map of Moland, and then the worksheet that accompanies this tutorial. First, before we look at calculating percent yield, let's look at some definitions. The theoretical yield, this is going to be what you calculate. This is the maximum amount of product that can be produced from a given amount of reactant. So this is the stoichiometry, the actual setup and calculation of what you would calculate to be your product, the amount for that product. The actual yield, on the other hand, is the amount of product that is actually produced when the reaction is carried out. We call this the experimental value. It is the value that you obtain in lab if you actually run this experiment. So the percent yield will be the ratio of the actual yield to the theoretical yield as a percent. So the equation for that is actual yield divided by theoretical yield multiplied by 100 equals percent yield. And so for this topic, for the percent yield, we're not doing anything new with stoichiometry. We are going to set up and solve for product just like we have done previously. It's just that we'll take this extra step and calculate the percent yield. So the way that this works is usually they will give you the actual yield, the amount that a student obtained in lab, and you'll have to find the theoretical yield yourself and then compare that ratio to find the percent yield. Let's take a look at this first problem. It tells us in this reaction of ammonia, and this 2 goes with it, 2 moles of ammonia yields 3 moles of hydrogen gas plus nitrogen gas. So it tells us if you have 12 grams of ammonia, and that's going to produce 1.87 grams of hydrogen, what was the percent yield? And so what it's telling us is that if you were given 12 grams of ammonia, it is going to decompose into an actual yield of 1.87 grams. And so we need to calculate the theoretical yield. And so I'm going to write that down here as this first step. Calculate the theoretical yield for H2. So if given 12 grams of NH3, what would our theoretical yield of hydrogen be? And so we're going to solve and think of your map of Moland. You first have to go from grams to moles, and then you can go from moles of one product to moles of another, and then use molar mass once again to find the mass. So we're given 12.0 grams of NH3. And we're going to calculate molar mass. And so I have that calculated already. It is 1 mole of NH3 is equal to 17.013 grams of NH3. So remember, this is the molar mass. Now we need to look at the mole ratio. We have 2 moles of NH3 to every 3 moles of hydrogen. And this came from our balanced equation. It's the mole ratio, which we get from the balanced equation. And now we are in moles of hydrogen. So all we have left to do is find the molar mass, which is 2.016 grams of hydrogen. And like I said, this is the molar mass, and so it is over 1 mole of hydrogen. And we can double check to see that everything cancels out. Grams of ammonia, moles of hydrogen, and we are left with 2.13 grams of hydrogen. And now this is the stoichiometry, so this is our theoretical yield. So now let's take a look at top. We're going to place our actual yield first, 1.87 grams of hydrogen, divided by 2.13 grams of hydrogen, and multiplied by 100. And this will give us a percent yield of 87.6% yield for hydrogen. So that is our answer for this percent yield problem. We have made the ratio of actual to theoretical multiplied by 100, and we have achieved 87.6%. Moving on to the next example. In this case, it tells us that we have excess hydrochloric acid and that it was reacted with 8.57 grams of calcium carbonate, and that's going to produce 3.11 grams of carbon dioxide. So once again, it wants to know what was the percent yield for this equation. And so for this round, we will need to write the equation and balance it before we can even begin to look at making these stoichiometric calculations. So let's start with the equation. We have hydrochloric acid. And it's going to react with calcium carbonate. And then we can see here we have an acid and an ionic compound. So you should be able to identify this type of reaction. This would be a double replacement reaction, and so you'll have hydrogen replace calcium, calcium replaces hydrogen, and our new compound would be H2CO3 plus calcium chloride. Now, I just want you to take a look. It's asking for carbon dioxide, and so that should remind you of something that we talked about recently with this acid. This acid will continue to decompose, and we know that when acids decompose, they decompose into water and a non-metallic oxide, which will be our gas. And so this is going to continue to decompose. H2CO3 will break down into water and carbon dioxide. Now we can balance the equation. I think all we need is a 2 right here. And that should be balanced. So now let's look at what we're given. It tells us we start with 8.57 grams of calcium carbonate. It's going to produce 3.11 grams of carbon dioxide. Once again, this is the actual yield from a laboratory experiment. And so to find the percent yield, we must go back to that first step, and we must find or calculate the theoretical yield. So let's get started with that. Remember, it is a stoichiometry calculation. Once again, we'll start with what we're given, 8.57 grams of calcium carbonate. And we're going to convert this to moles using molar mass. So I had calculated this previously, but I'll write a note down here that this was a molar mass calculation. Now that we are in moles of calcium carbonate, if we want to go from moles of calcium carbonate to moles of carbon dioxide, we must use the mole ratio. Remember, the mole ratio comes from the balanced equation. So we see that we have 1 mole of calcium carbonate to every 1 mole of carbon dioxide. And then our last step is to look and see, okay, we just need to find grams. We're going to use molar mass of carbon dioxide to find the number of grams. So 1 mole of carbon dioxide to the calculated mass of carbon dioxide, which is 44.009. This will give us 3.768 grams of carbon dioxide, and this is the theoretical yield. This is what we get from stoichiometry. This is our calculation of what we should have achieved. However, we know that these laboratory experiments aren't perfect, and so if we compare our theoretical to our actual, we see that the actual yield is a little bit less. And so let's make a calculation to see our percent yield for this equation. We're going to place our actual yield first, 3.11 grams of carbon dioxide, divided by 3.768 grams carbon dioxide multiplied by 100. And this should give us a percent yield of 82.5% yield for carbon dioxide. So once again, this shows us that the laboratory experiment was not a complete perfect reaction. We probably lost some product due to error. Maybe some of the product was left inside filter paper or inside of the beaker. Something might have happened, the reaction didn't go to completion, to where our actual yield is less than our theoretical yield.